Continuing with Exam 2, Part 2. We are asked to draw a circuit diagram for the Boolean expression f equals AB naught XOR C, all knotted. The circuit diagram should use transistors, NPN and PNP, a 5-volt power supply, and ground. So how did I go about solving this problem? Well, first, I chose to do a truth table. So my truth table is right here for the expression f equals AB naught XOR C naught. So we have the column for ABC. So these are all the truth table values for that. We have the truth table values for A naught, B naught, and C naught here. And then we have the truth table values for AB naught. So these are the values for that expression. And then I XOR those values, AB naught, with C, and these are the values I get here. And finally, I knot all the values that I got out of this expression, so basically it's just the inverse. And from this, then I can do what is now called a K-map. So here is my K-map. As you can see, I've highlighted it out in blue, green, and orange to match the equation that we're going to come up with. So in the blue column here, we have A, which is 0, so that's A naught, and we have B naught, C naught, and then we have B, C naught. So since B actually changes values here, we can ignore the letter B, and we can just go with A naught, C naught, which is this. Okay? Now for the orange value, since there's only one, we're going to have to require all three values. So this is A, B naught, C, so that's what we have here. And then in the green column, we have two values, and that is going to be B, since it stays positive, and C naught, since it's 0, and since A alternates between 0 and 1 for both values, we can ignore it. Now, this is not the only way to get to this expression. So let's look at another way. For that, we're going to look at the algebraic version of this process. So f equals AB naught XOR C knotted. So here we have the equivalence for n XOR, okay? So here's our XOR expression knotted, and here's the equivalent XOR expression broken out. So we have XY plus X naught, Y naught, okay? Now if we take P and we set it to AB naught, then we put it back into our original equation, we get P XOR C knotted. So that looks like this up here now, okay? So we just expand this out, which becomes PC P naught C naught plus P naught C naught, and then we put our AB back into the equation using parentheses. So we have AB naught C, and then AB naught naught C naught, okay? Now, because we have a naught here, we can expand this out again using the naught equivalence. So XY naught is equivalent to X naught plus Y naught, all right? So that then gives us this expression, which is AB naught C plus A naught B naught naught C naught. Okay, let me scroll up just a little bit here so you can see this, and you can see how I expanded it out. And since these two here basically just become a B, the next thing we can do is we can take our C and distribute it across our A naught and our B, which is what I did here. So we have A, B naught C, and then our A naught C naught plus B C naught, okay? So now, let's go back up to our key map, and here's that expression. A naught, C naught, A, B naught, C B C naught. And let's scroll back down here to after our math, and you can see that we have the same expression. So now that we have everything in just ands and ors, we're ready to start doing our circuitry. And our circuitry relies on NOT gates, NAND gates, NOR gates. Okay, so that's in the CMOS land. This is how we do a NOT gate. So we have A, B, and C, and I'm not going to draw out individual NOT gates for all A, B, and C. It's just too much work. So here's A prime, B prime, and C prime, just like we had in the truth table. And now we use a NAND gate to get the values of our A, B, C naught, or A, B naught, C, and our A naught, C naught, and our B and our C naught expressions. Okay, so we have PNP transistors at the top here because of the way the arrow is drawn, and then down here we have NPN transistors because of where the arrow is and how it's drawn. All right. And the other thing to note is this is 3 transistors for each one of these variables. If there were 4 variables, then we just draw another PNP up here, and then we draw another NPN down here. And if there were only 2, then we just knock off one of these. And that's how you expand and contract this NAND gate in order to add more variables. So we're at 3 for the first one, that's why I drew it out at 3. For the 2 variables here, we would just knock off one of these and reassign them to the appropriate values. We'll see that when I do the circuit diagram through KiCad. Okay, so here's our NOT gate. Oh, that's the other thing. So you'll notice that I have W1 NOT, W2 NOT, W3 NOT, and then all these are knotted. Well, that's because this is a NAND gate, not an AND gate. So any information we put in through here is always going to come out knotted, and we have to get rid of that. So that's where this NOT gate comes in, and we're going to pass these values through a NOT gate and just remove the NOT. Okay, now the last step of our equation was to OR everything. So here we have wire 1, wire 2, and wire 3 coming into our PNPs. And then down here we have the same wire 1, wire 2, and wire 3 going through our NPNs and doing an OR. And so just like our NAND gate, this is a NOR gate. So any expression we create is always going to be knotted. And in order to remove that knot, what do we have to do? We have to pass it through a NOT gate. And so we take our W1, W2, W3 all knotted, pass it through the NOT gate, and we get W1, W2, W3, which is our output for that function f. Okay, let's go test this. So to see whether or not this works, we're going to stop in circuit verse here first. And here is this function written out in circuit. So here's my AND gate, here's my XOR gate, and it is knotted. So there's my NOT. So originally this is an XOR with the double line here, and then the NOT at the very end. Okay, so as you can see at 0, 0, 0, it's true. We can actually make our life a little easier, and we'll go back and take a look at my truth table. So let's scroll back up here. So here is the truth table. Okay, so when A, B, and C is 0, we should have a value of 1. If we set C equal to 1, we should get a value of 0. So let's go do that. Let's go set C to a value of 1. And we got a value of 0. So what did I do wrong down here that is giving us a value of 1? Did I make a, so that's C, we have B naught, and we have A. So you can make a mistake. So let's correct this, and we'll go drop this off on A. There we go. And now we have 0. All right. So our circuit diagram now matches our function specification, and we can see that both values are 0. Let's go back and turn this off, make sure both values are 1. Yes, they are. Okay, let's go back to our truth table. And for that, the next set, we had B on, and that should be a 1. So let's try that. So let's turn B on, and it's still 1. Okay, and the third one, or actually fourth, so B and C are on, we should get a 0, and there we are. Back to our truth table, and we have A on, B and C are off, we should get a 0. We should only get 1s when C or B are on, but not both of them, and we should get a 0 when they're both on. So let's go test that sequence out. So right now, we're going to do 1, 1, 1, and we can see that they're off. So let's turn off B. We can see that we get a light here. And let's turn off C, and we have no lights on. Now let's turn on B, and we get lights. Okay, so this set of circuitry matches this set of circuitry, and both sets of circuitry are based on these equations. Okay, so that's the logic diagram of this answer. Now, let's go back and look at the circuitry for the NPN and the PNP transistors. For that, we have this diagram, and I apologize, it's a little small. You may need to explode your window to see the differences in all these, but in this column here, let's see if I can highlight this. I cannot. Okay. So in this column here are all of my NOT gates, and this is a PNP, and this is an NPN, and this is A to A naught. All right? And then we have A, B naught, C into wire 1 knotted. And in this column is all of our NANDs. Okay? So we have A naught, C naught into wire 2 knot. And then we have B, C naught into wire 3 knotted. Now, one of the things I could have done is I could have taken my knots and wired them directly in, but for the purposes of this video I kept them separate so that you could see that they are in a column, all being knotted. The next step in our circuitry is to OR them, which is right here. So we have wire 1, so here's wire 1, wire 2, wire 3. Wire 1 comes in, wire 2 comes in, wire 3 comes in. And then we have wire 1, 2, and 3 down here, and that produces an output that is knotted, okay, for wire 1, 2, and 3. So we take that, we pass it through a final knot to get our final output. And that is how you answer this problem. I hope you learned something. Have a great day. Bye-bye.